Hello students, I am taking an extra class today to compensate for the class which I had lost when I had applied leave. So let us continue with the discussion which we had in the last class. In the last class we had discussed the fixed bias configuration of JFET, and we had seen that there are two approaches. One is a mathematical approach and one is a graphical approach. The graphical approach is the easier one, whereas the graphical approach can have inaccuracies also. The mathematical approach is the accurate one, but the mathematical approach can be slightly difficult in case of self bias and voltage divider bias. It was easy in case of fixed bias, but we will not be using fixed bias because of the instability of the Q point, and this we had already seen in the case of BJT circuits. So today let us see the self bias configuration. You can see this particular circuitry. In this circuitry, there is no gate to source voltage at all. That means there is no gate bias at all. Now you may wonder, when there is no gate bias, how this circuit will work. The circuit will work because across RG, there is a resistor here from the gate to the ground. Across RG, there will be a negative gate voltage. That I will be showing you later on how that gate voltage appears across RG. So when compared to the fixed bias, in this particular circuitry, you don't have an additional power supply. In the fixed bias, we had used an exclusively different power supply to the gate. But here in the circuit, the power supply for the gate is absent. So our normal effort is that JFET will be on as soon as the supply voltage in the drain is given, and to turn it off or to make it half on and half off, we should apply negative gate voltage with respect to source. But here now, instead of having a negative power supply, we are simply connecting a resistor, and let us see how the gate voltage appears as negative in this particular circuitry. In fact, these are all some circuit techniques which our earlier scientists had developed, and we are using them even now. So let us see how negative gate voltage appears at the gate. So brief explanation: the self-bias configuration eliminates the need for two DC supplies. An additional resistor is introduced at the source terminal for the stability of the Q point, because if this RG is not there, we will not have DC gate voltage at all across the gate, and we cannot turn off the device at all as such, or we cannot turn off the device even half also as such. So this resistor is required. Now the controlling gate to source voltage is now determined by the voltage across the resistor RS introduced in the self bias configuration as shown. You might remember that we had introduced an emitter resistor across the VJT. Same way, now we are introducing a source resistor here. In the fixed bias, the source resistor was not there, the source was directly connected to ground. But in the self bias, as the name itself says, if there is voltage across this RS increasing, then the increase in this voltage will gradually reverse bias the source junction, and that is how the JFET is prevented to completely turn on or completely go into ohmic region. Now in the JFET's case, it is prevented to turn off also completely because of the introduction of the source resistance. That is the reason even in the case of BJT, we had called it as self bias, because the circuit is biasing itself just by introduction of a resistor at the emitter. Here in the same way, at the source there is this RS. And now we have to see across RG what is going to happen. Let us see that in the next slide. For the DC analysis, the capacitors can again be replaced by open circuits, and the resistor RG is replaced by a short circuit since gate current is 0. We already know in the circuit that there is no gate current at all. The JFET will not have any get to source current because it is a PN junction that is reverse biased. So considering that the gate current is 0, we can replace RG by a short circuit and we can replace capacitors by open circuit for the DC analysis. Now based on this, we are applying it this way. Look at this. Now the resistor is shorted and capacitors are open. If you apply KVL across this gate to source now, whenever this transistor is conducting, there will be a voltage drop across this RS, and as the gate is grounded now and as the source is at a positive potential now, we can easily find out that gate to source voltage is minus of the voltage across the RS. Look at this picture. Gate to source voltage is negative of the voltage across RS, that is indicated here as VRS. Now this simply means that the gate to source voltage is negative. That is what we wanted. And there is no drop across RG. Even though RG is present there, there will not be any gate current. So there will no voltage drop across RG, which means, I will show you again the previous circuit. Here the source is at a lower potential, source is at a higher potential and the other end of the RS is at a lower potential. Now that itself is connected to the gate. There will be no current flowing through RG. So effectively we should say that even gate is connected to ground potential. When gate is connected to ground potential, when the source is at a higher potential, when we measure gate to source voltage, when we move from gate to source, we are moving from 0 to VRS. And VRS is positive. That is how we get VGS as negative. Now these are all circuit techniques as I have been telling you. So now the current through RS is the source current IS, but IS equals ID. The source current and drain current are same. Therefore VRS equals ID into RS. That means the voltage drop across this RS is the drain current into this resistance. Applying KVL, minus VGS minus VRS equals 0. Positive to negative, again positive to negative. Let us put it as minus VGS minus VRS equals 0, or VGS equals minus VRS. This VRS is nothing but minus ID into RS. So the voltage that is across the source resistor itself is going to appear across the gate to source as a negative potential. That is how the transistor will remain in the mid region. Here we call it as saturation region. In case of self bias, unlike fixed bias, VGS is a function of the output current ID and is not fixed in magnitude. Please understand this. In case of fixed bias, we had the VGS or gate to source voltage which was fixed. That means we were applying a power supply to the gate. But here you can see that VGS is minus ID into RS. Means VGS is not a fixed voltage here now. When the drain current changes, even VGS changes. That means VGS is a function of ID. Even though RS is fixed, ID can change based on the value of RD. If ID changes, even VGS also changes. That is how we say that VGS is a function of ID. So when we go for a graphical analysis, we cannot have a vertical line having a fixed value. Now it will be varying. Let us see later on how, in spite of this particular equation, how we solve the Q point graphically. I'll explain that when I discuss the exercise. So, in case of self bias, unlike fixed bias, VGS is a function of the output current ID and VGS is not fixed in magnitude. A mathematical solution could be obtained by substituting VGS into Shockley's equation as follows. We already know that ID equals IDSS into 1 minus VGS by VP whole squared. Now substitute for VGS, it is IDSS into 1 minus ID into RS divided by VP whole squared. That minus into minus becomes plus. So ID equals IDSS into 1 plus ID RS by VP whole squared. Now this is a quadratic equation now. Earlier in the fixed bias, we had a linear equation. Now here we have a non-linear equation. That is why the mathematical solution will not be so easy here now. This results in a quadratic equation which can be solved for obtaining ID. You already know how to solve the quadratic equations. You already know that minus b plus 1 square root of b square minus 4ac divided by 2a. That quadratic equation can be applied here also, and this equation can be solved because we will know IDSS, we will know VP. Those are constants. We will be knowing RS also. IDSS and VP will be given by the manufacturer. RS is the one which we are going to decide. So we have to find out only ID. So it is possible to solve this equation. Now this is that quadratic equation if we have to reframe the equation in terms of ID itself, because we have to find out ID. From the upper equation, you cannot easily substitute it as minus b plus m square root of b square minus 4ac divided by 2a, because the upper quadratic equation is not in the standard form. Now we have to bring it into the standard form. We can expand this equation. I have already expanded this equation, and we get this form: id square into rs square into idss divided by vp square plus id into 2rs into idss by vp minus 1 plus idss equals 0. Now this is of the form ax square plus bx plus c. So this is id itself is now x square, this id itself is now x, this is now c. So rs square into idss divided by vp square itself is a, 2rs into idss divided by vp minus 1 is b, and idss itself is c. So that way we get a quadratic equation. Why do we need to use negative potential to gate even if we are using FET as an amplifier? This is the question. That means you have forgotten the basics of JFET. I have been repeatedly telling that JFET will be normally on, we have to turn it off. Unlike BJT. BJT will be normally off, we give a gate current, then we turn it half on to work it as an amplifier. But JFET is normally on. Please refer to the previous videos of the initial classes where I discussed the JFET's construction in detail. In between drain and source, there is a N channel, and as soon as you apply the voltage across this N-type semiconductor, current will start flowing, because N-type semiconductor is basically a conductor. Silicon in the pure form is semiconductor. Whenever it is doped, it is going to become a conductor there. So N-type is basically a conductor. As soon as you supply voltage, it will start conducting. That is why I have been telling JFET is normally on. Now we have to turn it off. For turning it off, we have to apply negative potential to the gate. So if you do not understand this, you will have to refer to the previous class videos again. That's all. Otherwise, I will keep on telling the same answer again and again. That JFET is normally on. We have to turn it half off by applying negative gate bias. That is why, because we apply negative gate bias, JFET cannot have a gate current at all. This I had discussed in the earlier classes. If you had become absent for some of the classes, you will have to refer to those videos. Now let me continue the discussion. We have this quadratic equation which is in the standard form. But you can look at this equation, how complicated this equation is. That is why I have been telling the mathematical solution can become more and more complicated when we go for self-bias and voltage divider bias. In the case of the voltage divider bias, this equation is still more complicated. That is why we go for a graphical solution which is easier for us. Even though there is a slight difference in the values which we obtain, still graphical solution is better compared to mathematical solution. Let us proceed with the analysis of this self-bias circuit. Applying KVL at the output side now. VRS plus VDS plus VRD minus VDD equals 0. There will be a drop across this RD, there will be a drop across the JFET between drain and source, there will be a drop across this RS. So VRS plus VDS plus VRD totally is VDD. Or we can write as VDS is VDD minus VRS minus VRD, because we want to find out the Q point. Q point means it is VDS and ID. So VDS is VDD minus VRS is nothing but IS into RS. VRD is nothing but ID into RD. But we know that IS and ID are one and the same. So we can write an equation for VDS as VDD minus ID into RS plus RD. It is a similar equation which we had obtained in the voltage divider bias also for the BJT, or self bias circuit for the BJT. It is a similar expression. But we know that ID equals IS, so VDS equals VDD minus ID into RS plus RD. Now Vs, the voltage across the source, is ID into RS. Gate voltage is 0 volts. Why? Gate is connected to ground anyhow. There is no gate current there. Even though that RG is there, there is no gate current there. So now gate voltage is 0 volts. Now you may ask again one more question. Let me go back to the slide. Let me go back to this slide now. You may ask the question, if the gate voltage is 0, then why are we applying RG at all? Can anyone tell me the answer? We say that there is no gate current, so the voltage at the gate is basically 0 volts. If the gate voltage is 0 volts, why are we connecting this resistance at all? Why don't we simply remove the resistance? Can anybody put the answer in the chat box? I'll wait for a few minutes.
Sir, could you repeat the question?
Yeah, the question is, when we take the gate as at 0 voltage, we don't have any gate current, so we consider the gate voltage as 0. In that case, why should we connect this RG at all? Because we are going to short circuit this RG in our DC analysis. Across RG there is no current. So why this RG is required?
Prevent AC signal going to ground.
That means gate cannot be connected to ground, right? Physically gate cannot be connected to ground. But as far as DC is concerned, gate should be taken as 0 volts, because source will be at a higher potential. So naturally VGS will be negative. Now if we don't connect this resistance RG, then at the gate there cannot be any DC potential at all. For that reason, we have to connect RG. So that is the correct answer. Yeah, Sayan has given the answer here, for the input signal to enter without being affected. Correct. Otherwise, if we connect gate to ground, all the signal will go to ground only. We cannot physically connect the gate to ground, but we want the gate to be at a 0 voltage as far as DC is concerned. That is the reason we connect this resistance at gate. Let me go to the next slides now. Yes, we were here. So Vs is ID into Rs, Vg equals 0 volts. Now Vd is voltage at the drain. Voltage at the drain is voltage across drain and source plus voltage at the source resistance. So Vd, voltage at the drain, is Vds plus Vs. Now Vds plus Vs can be Vdd minus Vrd. It is one and the same. Either you measure from the bottom to the top, or you measure from the top to the bottom. Now if you have to measure from the bottom to the top, voltage across the Rs plus voltage across the device is drain voltage. That is Vds plus Vs. Or when you come from the top, total voltage is Vdd minus the voltage across the drain resistance itself will be the voltage at the drain with respect to ground. So these you will have to remember. You don't have to memorize all these expressions as such, but if you remember the circuit diagram, automatically you will recall all these equations on your own. It is not necessary that you will have to memorize all these equations. But Shockley's equation you will have to memorize, you will have to remember. Now how to find a graphical solution? I have shown you the mathematical solution now. Mathematical solution is by means of using this quadratic equation, where we can find out ID using this equation. Later on, once we find out ID, we can easily find out VDS. And we can find out all other voltages in the circuitry. This is a mathematical solution. Let us see how to go for a graphical solution. The graphical approach requires that we first establish the device transfer characteristics. Now, you already know how to have a device transfer characteristics by using those 4 points. VP will be given, IDSS will be given. You will have one point here where VP you mark in the x-axis and IDSS you mark in the y-axis, because whenever IDSS is there, VGS will be 0. Whenever VP is there, ID will be 0. So that way you got 2 points, one in x-axis, one in y-axis. Another thing is when you have 0.3 VP and 0.5 VP, correspondingly you will have IDSS by 4 and IDSS by 2. So based on that, we can actually construct the transfer curve. Now in the transfer curve, last time we had one vertical line, and wherever the vertical line cut the transfer curve, that was going to be the Q point. Now here, VGS is a function of ID. So we do not have a vertical line. Still, we have to draw a line now in such a way that it will cut the transfer curve. How to obtain that line? Let us see that now. Equation VGS equals minus ID into RS defines a straight line on the same graph, right? Get to source voltage is a function of IDRS now. Now this is nothing but of the form y equals mx plus c, where c is 0. So this is a linear equation. This is an equation of a straight line, but it is not a vertical line because VGS value is not fixed. VGS is dependent on ID. Now we have to have at least 2 points here. If you have to mark a line here, at least we should have 2 points here. So the first point is origin itself. Why? When ID is 0, VGS is 0. So we can immediately find out 1 point for the straight line. We need another point now. See, 1 point already is there. VGS is 0 volts, ID is 0 volts because VGS is minus of ID into RS. When you substitute ID equals 0, you will get VGS 0. We got 1 point. That means the straight line which we are going to mark is going to pass through the origin. Okay. Let me admit the student. Fine. Now we got 1 point for the straight line. We need one more point now. What else we know now? We know the value of RS and we know IDSS. Why don't you substitute a value as IDSS by 4 or IDSS by 2? Because we know that value. And we can find out VGS that way. When we find out VGS that way, we can get another point there. And we can join those 2 points. That's all. You already know IDSS. And you already know IDSS by 4 is how much, IDSS by 2 is how much. All that you will be knowing. Simply substitute that here. You will get a corresponding VGS. Now that point x-axis you know, this point y-axis you already know. You can mark that point somewhere here and you can join with the origin. When you join it with the origin, you will get a straight line. Wherever the straight line cuts the transfer curve, there you will get the Q point. So let us see how we obtain this. To identify the 2 points, to draw the line, apply ID equals 0 amps, which gives VGS equals minus ID into RS equals 0 into RS equals 0 volts. You got the origin now. Now the second point requires that a level of VGS or ID be chosen. We choose a level of ID equal to 1/2 the saturation level. You can choose IDSS by 2. You can also choose IDSS by 4 also. All of them will be same actually because the straight line will have all these points. Now here it is told we choose a level of ID equal to 1/2 the saturation level. So let us say we choose IDSS by 2. Now when we choose ID equals IDSS by 2, VGS is minus ID into RS equals minus IDSS into RS by 2. You know the value of RS, you know the value of IDSS, you get the value of VGS. Now mark this particular point in this graph and join that with the origin. You will get one straight line and that will cut the transfer curve. Look at this. If you mark this IDSS by 2, IDSS by 2 will correspond to this VGS equals minus IDSS into RS by 2. Now that point and this point that is coming here. Now join this point with the origin here. It will cut through the transfer curve and you will get the Q point here. That Q point's coordinates you can easily find out as VGSQ and IDQ. Now once you find out this IDQ, you can substitute it in all the expressions which we had derived in the previous slide and you can find out VDSQ. That way the graphical solution is obtained. Now please understand, for the graphical solution to be obtained, we need at least 2 points for the straight line. We already have the origin and we will have to get another point by substituting either IDSS by 2 or IDSS by 4 or any other value between the 0 and IDSS. Because all those points you will get across this line itself. Even if you choose IDSS by 4 also, you will get a line somewhere here. For IDSS by 4, you will get a line somewhere inside. And if you get, let us say, IDSS into 3 by 4, then you will get a line somewhere outside, somewhere here. Anyhow, you will be getting 2 points. You join those 2 points, you will get this straight line. It is not mandatory that you will have to choose ID equal to 1/2 only. You can choose any value of the drain current which is between 0 and IDSS. And you will correspondingly get another point in the x-axis. Join that, you will get this straight line, and wherever the straight line cuts the curve, you will get the Q point. Now let us have a solution for this particular exercise. Determine the following for the network using the graphical method. We will not go for the mathematical method because we have to solve that quadratic equation. We are not interested that way because anyhow the error is going to be hardly a few millivolts. It does not matter much for us. So let us solve this using the graphical method. Even in the exam or even in the test, you will not get the mathematical methods question. For the fixed bias, you may get mathematical method as well as graphical method because there it is quite easy. For the self bias and for the voltage divider bias, you will not get the exercises to be solved using the mathematical method. We will be using only the graphical method. So now, look at this equation. Look at this circuit diagram where RS is given 1 kilo ohms, RD is given 3.3 kilo ohms, IDSS is given 8 milliampere, VP is given minus 6 volts and RG is given 1 mega ohms. Capacitors are not shown because this is for a DC analysis. Now can any of you put an effort now? Approximately, can you tell me the transfer curves, points? You already have 2 points for the transfer curve. You will have to find out the other 2 points, choosing 0.3 VP and 0.5 VP. Now can any one of you try? If you say yes, then I will wait. You don't have to try the complete exercise, but can you at least try to plot the transfer curve? And for the line, I will help you later on. Okay, Sayan has told yes, sir. So let me wait for a few minutes until Sayan or anybody else tells me the coordinates for the transfer curve. I will help you in remembering those equations. Corresponding to 0.3 VP, it is IDSS by 4. Corresponding to 0.5 VP, it is IDSS by 2. Remember that. Here IDSS is given 8 milliampere, VP is given minus 6 volts. Using this data, you can plot the transfer curve. So Sayan has given the answer minus 2 and 0 on x-axis for ID equals IDSS by 2. For 4 milliamperes, you will get IDSS by 2 corresponds to 0.3 Vp, right? Or 0.5 Vp. One corresponds to 4 milliampere, one corresponds to 2 milliampere. So it is,
1.8, comma 2.
yes, correct. This minus 6 volts into 0.3 is 1.8 and minus 6 volts divided by 2 is minus 3. So using all those coordinates, now we have totally 4 points. Using all those coordinates, we can plot the transfer curve. From the given values of IDSS and Vp, the characteristic curve can be plotted as shown. Further, the gate to source voltage is determined by Vgs equals minus ID into Rs. For ID equals 4 milliampere, Vgs equals minus 4 volts. From this value, a straight line can be drawn as shown. So I am showing you the solution. This is the transfer curve now. Using IDSS and Vp, here he has shown only one point. Actually, only one point is not sufficient. You have to have one more point. Now, this is corresponding to IDSS by 4 and minus 3. This is IDSS by 4 and 0.5 Vp. For IDSS by 2, you will have 0.3 Vp. That means for minus 1.8 volts corresponding to 4 milliampere, you will have 1 point somewhere here. 1 point somewhere here, 1 point here. Now, without this point, here he has approximately drawn anyhow. But it is better that you calculate all the 2 points and then join this transfer curve. Now, already we know that origin is one of the points for the straight line, and we already, if you substitute 4 milliampere, we get Vgs equals minus 4 volts. So, corresponding to 4 milliampere here and for minus 4 volts here, we will get a point somewhere here. See, this 4 will come here, this minus 4 will come here, we will get a point somewhere here. That point and the origin, when we join, we will get a Q point. Now, this is that. Corresponding to 4, you will have minus 4. In fact, you can get one more point also. When ID is 8 milliampere, when ID is maximum, it is corresponding to this Vp, right? Minus 8 volts. Okay. That way, when ID is 8 milliampere, it can be minus 8 volts. Because minus 8 into Rs. That Rs is given as 1 kilo ohms. You will get minus 8 volts. Or you can have one more. IDSS by 4 is 2 milliampere. 2 milliampere into 1 kilo ohm is minus 2 volts. That way you can get multiple points. So when you join all of them, you will get a straight line. There is a question. What is the question? But sir, in the formula, Vgs equals minus IDS into Rs. If ID is IDSS by 4, then Vgs would be minus 2. So in the graph, how can it be minus 3? No. That minus 3 is corresponding to transfer curve. Don't get confused with the transfer curve and the straight line. Transfer curve we have to plot using the Shockley's equation. Please remember that. This IDSS by 4 is corresponding to the transfer curve. But here this IDSS by 4 is corresponding to the straight line. They are not the same. Okay. I hope you got it now. Did you get it? Okay. First you have to plot the transfer curve, then on the transfer curve you have to plot this straight line. I am showing you separately here, only for you to understand. Otherwise, what we are going to do is we are going to draw this line on top of the curve itself, taking all the other points of the straight line. Now, look at this particular picture. Now that transfer curve and the straight line both are together in this picture, and this is where the straight line is cutting the transfer curve, and you will get a Q point where IDQ corresponds to 2.6 milliamperes and VGSQ corresponds to 2.6 volts. Because we are going to plot it in the graph, we can get an accuracy only for a single decimal point. So we get both same, VGSQ and IDQ we get both same, because Rs is there 1 kilo ohms now, right? due to which we get this Q point in this manner. Now we got this ID, we can substitute the value of ID in all other expressions for getting VDS now. So the resulting operating point results in a quiescent value VGSQ equals minus 2.6 volts. So at the Q point, IDQ is 2.6 milliamperes. So now VDS equals VDD minus ID into RS plus RD. This equation you should remember. Simply visualize the circuit diagram once again. When you visualize the circuit diagram of the self bias once again, at the top there is the drain resistor, at the bottom there is a source resistor, in between there is the JFET. So if you have to find out VDS, it is VDD minus ID into RS plus RD. Substitute all the values, you will get VDS as 8.82 volts. Now when you get this value, the next one is we want to find out the voltage across the source. VS is ID into RS. ID is 2.6 milliampere, RS is 1 kilo ohms. So you get the source voltage as 2.6 volts. Naturally, as the gate is at a zero potential, VGS is minus 2.6 volts. That is proven here anyhow. Get to source voltage is a negative voltage, due to which now the JFET is in the middle of the load line. Now for the JFET, we call it as saturation region. Please remember that. Even though JFET is half on and half off, we call this region as saturation region only, because the terminology in the JFET is different and the terminology with the BJT is different. So we get a source voltage which is 2.6 volts. In fact, when we get this VGSQ equals minus 2.6 volts, we can straight away write VS as 2.6 volts because they are opposite of each other in sign. Next point, VG is 0 volts. We already know. Gate voltage is 0 volts. That we already know. Lastly, VD we have to find out. VD is VDS plus VS. Drain to source voltage plus source voltage, that is 8.82 volts plus 2.6 volts equals 11.42 volts. This is one way. Another way, you look from the top side. VD equals VDD minus IDRD. You substitute that way, then also you will get 11.42 volts only. In Kannada we say Aliya alla Magalganda. And in Hindi we say, Hindi में क्या बोलते हैं, brother in law को पता नहीं. In English we say it is brother in law, nothing but son in law, not brother in law. Son in law, nothing but my daughter's husband. So in the same way, both VD expressions are one and the same. One is looking from the bottom side, one is looking from the top side. We get the value as 11.42 volts. So now this was an equation, this was an exercise using the self bias. Let me briefly discuss the voltage divider bias now, which is similar to self bias, but with the two resistors at the gate. I will briefly discuss this now. I will be discussing this once again in the next class. This is the voltage divider bias, where you already know that we had all these four resistors in case of BJT also, and we had gone for this voltage divider bias for the sake of stability of Q point. There we wanted to ignore IB. Now here the thing is, when there is no gate current itself, why should I have this R1 and R2 as a voltage divider bias? We can have a single resistor which we had earlier in the self bias, right? We can have this resistor in the self bias. Why should I have the two resistors now? In what way it is going to be having an advantage? Because anyhow gate current is 0. Now let us see what is the advantage of having voltage divider bias. The circuit is similar to that of BJT as that of self bias. Graphical analysis is preferred here, as the mathematical analysis is more complicated. The mathematical analysis in this circuitry is much more complicated than that of self bias. There we were getting a quadratic equation. Here we will get an equation which is more complicated than that previous equation. I will show you that equation. Now for DC analysis, anyhow gate current is 0. So now here it is easy for us. We don't have to worry about approximate analysis and accurate analysis as we did in BJT. Here there is nothing called approximate analysis because gate current is not at all there. We can straight away go for a DC analysis. All the capacitors, including the bypass capacitor CS, have to be replaced by an open circuit equivalent. We already know that. VDD can be separated into two equivalent voltage sources to permit a further separation of the input and output regions of the network. We can write the VDD separately here from R1 to gate to R2 and again from VDD to drain, then this way. We can have two separate networks only for the sake of our analysis so that we can easily deduce the value of VGS and we can easily deduce the value of VDS later on. Now, we can simply separate the circuit like this. If we have VDD here, R1, R2, we have VDD here, RD and RS here. So, when you look at the input side, anyhow gate current is 0 ampere. So, we can easily find out VGS now. Gate to source voltage is nothing but VDD into R2 divided by R1 plus R2 because it is a voltage divider network. So, the voltage at the gate is nothing but total current flowing through this R1 and R2 is VDD divided by R1 plus R2 because there is no gate current here. Current through R1 and R2 is VDD divided by R1 plus R2 and we want to find the voltage across R2. So, VDD divided by R1 plus R2 into R2, that is nothing but VDD into R2 divided by R1 plus R2. We got the gate voltage there. It is not gate to source voltage. Please remember, it is not VGS. It is VGG or we can say it is VG itself. Gate voltage with respect to ground. Later on we will find out VGS by applying KVL to the output side also. At the output side we can simply apply KVL which is VDD equals IDRD plus VDS plus ISRS or IDRS. So we get the same equation as the previous circuit. That means VDS equals VDD minus ID into RD plus RS. It is going to the same equation because as far as the output is concerned, there is no difference in the circuitry. So now we are applying this analysis and since IG is 0 ampere, applying KCL, we have IR1 equals IR2, Kirchhoff's current law. IR1 equals IR2. Using voltage divider rule, the voltage VG is given by VG equals R2 into VD divided by R1 plus R2 as I have been telling you repeatedly now. Applying KVL at the output side now, or we can apply KVL at this particular loop, we have VG minus VGS minus VRS equals 0. We want to find out VGS, right? So, there is VG here at the gate, then VGS here, then we have VRS here. So, VG is nothing but VGS plus VRS. Is it so? Wait a minute. Let me not confuse myself, let me not confuse you. Apply KVL here. Now, we have a voltage drop across R2. Current is going from VDD to ground here. So, this convention as plus and minus is correct. Again, there is a voltage drop across gate to source, that plus and minus. Again, across RS, there is plus and minus. So, when we apply a KVL, negative to positive, positive to negative, positive to negative. That way, negative to positive is taken as positive, positive to taken as negative. So that way, VG minus VGS minus VRS equals 0 or VGS equals VG minus VRS. If you bring this VGS outside to the other side, you will get VGS equals VG minus VRS. VG is obtained by the upper equation. Now, substituting for VRS, VRS is nothing but IS into RS is nothing but ID into RS. So, finally, VGS equals VG minus ID into RS. Remember this, in the previous circuit, we had an expression where VGS equals minus ID into RS. That was a straight line. Here, we also have to go for a graphical analysis in this voltage divider bias, but the equation is slightly different. It is VGS equals VG minus ID into RS. Now, equation of VGS is still the equation for a straight line, but the origin is no longer a point in the plot of the line. Why? Now, this is in the form of y equals mx plus c. In the earlier case, it was y equals mx. Here it is y equals mx plus c, where origin cannot be a point here. Now we will have to find out a method in which how to plot the line now. We have to find out all the points on our own. By default, we will not have any single point. We will see that in the next class. So the quantities Vg and Rs are fixed by the network construction. Vg is fixed, Rs we already know. Vg is fixed because R1 and R2 are fixed. Substituting for Vgs in the Shockley's equation, the expression for Id is obtained as like this: Id square into Rs square into IDSS by Vp minus Id plus IDSS into 1 plus Vg square by Vp minus 4Vg by Vp equals 0. You can see this equation, which is much complicated than the previous equation. This is also in the form of ax square plus bx plus c, but here b is 1. You can see this is minus id, so b is minus 1, b is minus 1, a is rs square into idss by vp, c is idss into 1 plus vg square by